Thank you. So hello, everybody. First, I'd like to thank the organizers for giving me the opportunity to speak here today. It's a real honor. As Tobias just mentioned, I'm Rebecka Sax, a PhD student in the group of Hugo Spinden in Geneva. Sorry. Yeah, it's on.
Could you bring it up a little bit higher?
Excuse me. Do you hear me better? Yeah? Okay. I can speak louder. Okay. Now? Yeah, okay, cool. So, right from the Quantum Technologies group at the University of Geneva and the group of Hugo Spinden. So today I'll present you some implementations that we have done with our high-speed QKD system with the goal precisely to remove some of the roadblocks for smooth integration and utilization in real-world networks. So first slide, I'm just going to show a map. So just to present more or less where we are, Switzerland here, Geneva is where we've been doing these experiments, and we're around just about here, other side of the Atlantic Ocean. Okay. So first, I'd like to identify some of the roadblocks for doing these, for doing a good deployment of QKD. So this is an experimental talk. I'll talk about some of the experimental problems. So first of all, we will want a smooth fusion of our QKD systems in the existing fiber optic networks. So this will probably consist of combining the quantum and classical channels in one fiber. Then we have the question of high secret key rate production. So in order to have an information theoretic secure communication, we would want our keys to be used with one-time pad, and the higher, well, to have high bandwidth, we need high secret key rates. And finally, our systems, they should be low cost, mass-produced, scalable, practical, and so on. And this will most likely happen with the help of integrated photonic circuits. So this will correspond quite well to my outline today, where I'll first start with presenting our QKD protocol, namely the 3-state time-bin BB84 protocol with 1 decoy state. And then I'll follow the list that I just showed you. I'll present you the implementation of this protocol in a network environment. Then I'll discuss the same implementation, achieving as high secret key rate as possible. And then finally, I'll present you our high-speed integrated QKD system. So going first into the protocol. So we encode our qubits in time bins. So each qubit consists of 2 possible bins, where we would say we would have either a pulse in the early time bin or in the late time bin. Okay, so these are our qubits. We can encode, so we have to encode in either of 2 bases, either the Z basis, or the X basis. So any qubits encoded in the Z basis will be used for the raw key. The Z basis, we have the state either 0 or 1. The 0 state consists of a qubit with a pulse in the early time bin. We can associate this to bit 0, and the state 1 consists of a pulse on the late time bin, and we can associate that to bit 1. Now we use the 3-state time bin, and so in the X basis, we only need the plus state, where here we have a pulse in the early and in the late time bin, right? Then to be safe against photon anomaly splitting attacks and also to improve our performance, we use the 1 decoy state protocol, meaning that we encode these 3 states with 2 different mean photon numbers. So just a word on the 1 decoy state protocol. So we use this as opposed to the 2 decoy state one, as in, so on the distances we use for the experimental distances, say we use, it has a similar performance, even slightly better in terms of secret key rate, and also, so in a finite key scenario, this is, and also experimentally implementing the one decoy is a bit easier. So we only need one decoy instead of two. Okay, so now going into the experimental setup, how we set up our QKD protocol and how we actually implement this. So on Alice's side, our goal is to produce single photon states and encode them. So here we use a gain switch laser at 2.5 gigahertz. So here we will have a stream of pulses, which will then enter our imbalanced interferometer. The delay line is of 200 picoseconds. So this means that here we will create our qubits, so a stream of qubits, and each early and late pulse are separated by 200 picoseconds. Okay. Then we have an intensity modulator where we can encode our photons. So this means that we randomly encode one of these 6. We place dispersion compensating fiber to pre-compensate for any chromatic dispersion that would happen in the fiber on the way from Alice to Bob. And finally, we have to attenuate down to single photon level with a variable optical attenuator. Okay, and then we have what we have wanted on Alice's. Depending on the protocol, we would place more or less single mode fiber in between, and then we go to Bob's. So Bob consists of a passive beam splitter, where part of the light will go to the Z basis detector. So here, the detections will be relatively straightforward as a time of arrival, and we would associate the detection to either the bin, the early or the late time bin, and then to the bit 01. So here we will get our raw key. So then detections that would pass either like more to the X basis detector will pass first through an imbalanced interferometer, which is identical to the one on Alice's side, meaning with a 200 picosecond delay line. And then we set the relative phase of the two imbalanced interferometers such that the central interfering peak of the X basis states that enter here will be destructive in this detector. So here in the X basis, these detections are used in an intuitive way to monitor any eavesdropping attempts. Okay, and then Alice and Bob, they of course have to be synchronized. This is done via service channel, where we also here perform all the post-processing. Okay, so now for the first implementation that I'll present to you is this protocol in a network environment. So first, some motivation. Fiber optics communications is widespread across the world and also in metropolitan networks. So it would be very useful to be able to come with your QKD system and plug it in your city and be able to communicate either between buildings in the city or maybe not so far apart cities. However, in general, when one would perform a QKD experiment in the lab, one would have dedicated fibers only for quantum communication. This is very expensive. So if we want to do this in a real-world setting, it's expensive to rent, maintain, and even place such a fiber for QKD. So a good idea would be to merge the quantum channel with the classical channel that already exists. Okay. So how is this done? So in classical communications, classical channels are merged via wavelength division multiplexing. So very standardized technique. So this consists of placing your channels in a specific wavelength, which are defined via the International Telecommunications Union, have defined specific wavelengths where one could place this. So for example, one can so they're defined via, for example, the coarse wave division multiplexing, where here we have channels that are placed 20 nanometers apart, or through the dense WDM, where here the channels are more densely placed at around 0.8 nanometers. One can also define bands where these channels live. And so the most common bands are the C band and the O band due to their low propagation loss here. So actually, just to mention, so in the C-band, one would have around 0.2 dB per kilometer of propagation loss, whereas in the O-band, this would be more 0.3. And so actually, in the classical channels are most often placed in the C, maybe even L band. So now the idea would be to place your quantum channel in one of these bands and then leave the classical channels where they are. Like this, you only have to occupy one predefined channel instead of having a complete fiber for yourself. Now, it's not as easy just to do that. There are some problems that come with doing precisely this. So on average, so the average power per channel in a classical channel is above a milliwatt, probably quite more. Whereas that would be in a quantum channel would be less than a nanowatt, probably even less. And so there's some problems here, mainly, so any light, any power from the classical channel that arrives on the quantum channel will be seen as an increase in errors, which if they're too big, then we would have a high enough QBER such that a secret key rate would not even be able to be produced. So this is the main issue, main problem that one has to tackle when performing precisely this WDM. So what are these, what effects happen? So for example, I'm gonna have imperfect isolation between the channels. This is a relatively easy fix, maybe one could say. And so one would have to think of proper filtering and isolating between the channels. Of course, the price to pay would be loss, extra loss by adding more filters. So this is something that, okay, one has to think about a bit carefully, but still one can try to place oneself for a board, or yeah, there are other techniques. Other problems, which are a bit more complicated, are problems like Brillouin scattering or Raman scattering. So this is scattering, which would, so for example, these effects would create a photon that would live in another, well, which would have a new frequency, and which would be, if we're unlucky, exactly the frequency of the quantum channel. And this cannot be spectrally filtered because we're in the quantum channel. And so these are effects that have to be thought about. So for example, the Brillouin scattering. So the scattered photon will have a new energy of only maximum 10 gigahertz. So to have negligible such scattering, it's enough to place oneself, place a quantum channel at a minimum of 2 DWDM channels apart from the classical channel. However, Raman scattering is much broader. And so this has to be thought about how to best still perform QKD with this still quite present. So this would be the main contribution to noise. So going further into detail about now Raman scattering. So here are measurements that were performed in our group. So here we have on the y-axis the Raman scattering cross-section as a function of the wavelength. So here we have the classical channel in the C-band at 1550. And we can place the quantum channel either also in the C-band, like we have here on the right, or we can place it in the O-band, like we have on the left. Okay, so at 1310, or we place it also around 1550 at another ITU channel. Now we can start by looking at this graph here. When the quantum channel is in the same band as the classical channel, we have first a high peak of this scattering cross-section. So this is due to the elastic Raman scattering, which would be at exactly the same wavelength as the classical channel. Then we see the Stokes and anti-Stokes scattering peaks, and a slight decrease when we go away from the wavelength. We can see it's a bit asymmetric, and so it would be maybe better to place a quantum channel rather lower lower in frequency compared to the classical channel. Okay, and then if we look at place the quantum channel in the O band, the main difference that we see is that here we have 3 orders of magnitude difference in Raman scattering cross-section if we place the quantum channel in the O band, so at 1310 nanometers. So maybe like this, it would look a bit straightforward, that it would be much more advantageous placing the quantum channel in the O band, keeping the classical channel in the C band. But okay, as we will see, it really depends on the network configuration and what distance and what classical pump power one would have. Discuss about more of this later. So next thing one can think about is in which directions do the classical and the quantum channel propagate. So are they co-propagating? Are they going in the same direction? Or are they counter-propagating? Are they going in opposite directions? And so the Raman scattering is isotropic, meaning that we would have as much forward scattered light as backward scattered light. So here we have the Raman noise power as a function of the length of the fiber. So at very short distances, the amount of noise power in the co-propagating and counter-propagating case is essentially the same. Now in the co-propagating case, we will have a decrease in Raman noise power. This is because of 2 reasons. So here in the co-propagating case, this means that the laser of the classical and the quantum channel on the same side, and then here we have our quantum detector. And so one reason would be that the amount of classical power will decrease due to loss. And so the amount of possible Raman scattered light will also decrease. So this will be nonlinear. And secondly, the amount of noise power that was created in the beginning, this is the most amount of Raman scattered noise power would be in the beginning, will also experience loss arriving at the detector. So we will have a decrease in this noise power with an increase in distance. For the counter-propagating case, we will see an asymptotic increase. And this is because the noise power, the noise that's created in the beginning, will always be the same. It will just be backscattered. This distance doesn't change. And then adding any extra fiber distance will not increase that much the noise power because of the same reason of propagation loss of the classical channel. So okay, so it's from this it can be concluded it's more advantageous placing oneself in a co-propagating case. So quantum channel and classical channel in the same direction of propagation. So this is precisely how we will set up our setup. So we will place our setup. So this means that we'll have the classical channel in the C band, quantum channel in the O band in a co-propagating scheme. Okay, we will also see that this is particularly advantageous in a realistic scenario, which we're interested in this case, meaning a scenario where we don't only have loss due to fiber, due to propagation in the propagation loss in the fiber, but also due to so external loss due to maybe in and out coupling that you would maybe have in a real world network where you have to couple out, couple in. Maybe some components are more lossy than others. And in this situation, it's particularly advantageous to place the quantum channel in the O band because here we have loss, which will be the same for the C and O band. Okay, so now we will see the experimental setup. So in terms of QKD protocol, Alice and Bob are really essentially the same. Only difference being to what I showed you just before. So the only difference being that the laser of Alice, so we're working here at 1310. Okay, so in terms of QKD, this is the same of Alice. Her qubits are multiplexed via CWDM with the classical channels. So here, the classical channels, we use 13 classical channels, which are multiplexed with a DWDM, amplified with an iridium doped fiber amplifier, and then multiplex with this quantum channel with the CWDM. Okay, so we place ourselves in 2 different scenarios. The first one, which I present here, is a long distance link. So around 95 kilometers of single mode fiber between Alice and Bob. So we pass through here. Via second CWDM, we will demultiplex. So the classical channels will will be demultiplexed with the quantum channels. The quantum channel will continue through here, and then here we'll have the QKD port of Bob. So we place an extra fiber spool, another CWDM, and a fiber Bragg grating to improve the resilience against the Raman scattering, so to filter out as much as possible the noise that we can. Right, so this is for the long distance link, and then for the realistic link, we have the same loss. However, this consists only of around 50 or something kilometers of fiber, and then we add 15 dB of extra loss. So this could simulate some network environment. Right, and then for the results that we obtain, so here we have for the two different distances, for the only fiber link, we send in around 9 dBm of classical power. We receive around minus 2.1 dBm, and we are really push ourselves to the limit and achieve 42 bits per second of secret key rate. Now in the realistic link, we add this 15 dB loss with 51.5 kilometers of fiber. So here we managed to send in 16.7 dBm on classical power, receive around minus 11.8, and we achieve 172 bits per second. So what we further did was to kind of compare different works, including our work, because one can really place oneself in either the quantum channel in the C-band and the classical channel, have them at different, in different bands. And so here, we have the launch power of the classical channel, and then here we have the fiber length. And so these are different works which also perform WDM QKD, either CV or DV, and in a different choice of bands at different classical powers. So, and what we see here, the green is a simulation of our experimental setup. So this work, the 95 kilometer fiber result is this point here. So we can conclude that for low fiber distances and high classical launch power, it's advantageous to use CVQKD used with the quantum channel in the C band. Then we can see that at medium distance fiber lengths, at still quite high classical launch powers, it's useful to use the DVQKD in the O band. Then if we go to the rather extreme case with the fiber length, long fiber length, and low classical launch powers, it's yet again probably advantageous to place oneself using DVQKD with the quantum channel also in the C band. Right. So that was more or less it for the network implementation. Now I'll go towards our high secret key rate QKD implementation. So this was work that was done in collaboration with Idée Quantique in Geneva, as well as Hochschule in Lucerne. So first, some motivations. So the US Federal Communications Commission, they suggest a bandwidth of 6 megabits per second per user for an encrypted video conference. So this would mean if you want to use an information theoretically secure communication, we would need precisely the secret key rate per user. So this would mean each of us during our phone call a few years ago would need to have the secret key rate. So the goal of this work was to see how high secret key rate our system could achieve. So some necessary conditions to perform a high secret key rate exchange are firstly on the detector side. So we have to be able to count at ultra high count rates, at low timing jitters and high efficiency and low recovery time. So this is something that we place a lot of efforts on. We also have to be able to perform the sifting at high rates and the real electronics. So this has to be able to follow at the same speed, which is the same for the post-processing as well as the real-time privacy amplification. Okay. So for the experimental setup, I show again the exact same setup of our QKD that I showed you in the beginning, because we don't do many changes. The main change we do is on, so the beam splitter on Bob's side. Here we heavily bias it towards the Z basis detector because we want to achieve as high key rate as possible. So here we have a 99:1 splitting ratio. And then we use here SNSPDs to be able to count at ultra high count rates, have low timing jitters, low dark count rates, etc. And more precisely for the Z basis detector, we use a multi-pixel SNSPD. And finally, so here I'll show the full experimental setup where I presented to you just the optics here. And additionally, we made use of in-house made constant fraction discriminators in order to actually lower the timing jitter that we obtain from our detectors, from the whole readout. And additionally, we use a second FPGA on Alice's side to be able to perform the error correction at high rates. So going to the detectors. So before I forget, so there's a talk by Giovanni Resta that worked on this project on Friday that will go more in detail about this. And so we use a multi-pixel SNSPD in the Z basis. So this means that we have 14 pixels that are independently biased, that are interleaved in this very nice geometry. And so here we see the detector placed here. So this is all cooled down at around 0.7 Kelvin. So this geometry is advantageous for two reasons. So firstly, we will have a uniform probability of each pixel to be to receive, to have a click to detect, and also the fact that we have 14 pixels reduces the length of each nanowire, which is actually which will actually lower the recovery time of our detectors. Okay. So here are some. Here we see some performance of our detectors. So we have the system detection efficiency on the y-axis as a function of the count rate on the x-axis. So for the Z basis detector and for the X basis detector. So maybe first remark to make is that the scale of the two graphs are not the same. So in the Z basis detector, we count at, well, we count for both at high count rates, but especially at the Z basis detector. So we place the experiment we place in two situations, one at 100 kilometers of fiber between Alice and Bob, and another one at only 10. So at this shorter distance, we really push our Z basis detector to the limit. So this would correspond to this point here. Here we count at around 330 megacounts per second. And so, but still at a relatively high efficiency of around 64%. Right, and so we see a decrease in the jitter at a higher count rate. This is because we will have a higher probability to click when the bias of the detector is not fully recovered. So the efficiency is slightly lower, right? Okay. Also, we will have on the decrease in jitter, which we see here, will also be because we have more frequent detections. And so there will be a bigger variation in the amplitude of the detections. Right. So going here to the results. So as I said, we place ourselves in two configurations, where for the 10 kilometers of fiber between Alice and Bob, we achieved a Cooper Z of around 0.4%, phasor rate of 0.8%, and a secret key rate of around 3.6 megabits per second. So this was work that was published in Nature Photonics back to back with this work here of Lee, which will be presented this afternoon. So, great. Okay. Now, for the third part of my talk, I'll present to you the high-speed integrated QKD. So this was work that was done in collaboration with the Politecnico in Milano and the CNR IFN also in Milano, as well as ID Quantique in Geneva and Sequoia in Berlin. Okay, so some motivations I already told you before, but using integrated photonics will allow for low cost, small footprint, mass production, high reliability, low power consumption, and many more advantages depending on the material you would use. So here, the goal is to implement exactly this setup in using integrated photonic circuits. So as an example, I show you here are some components of our fiber-based transmitter, notably the interferometer, intensity modulator, variable attenuator, digital to analog converter, and RF amplifier, which are now integrated or replaced somehow in an integrated transmitter. And so this is a to-scale image, if you want. So there is definitely a reduced footprint when doing this. So the transmitter Alice, which we use, is based on silicon photonics, has a very small footprint. So here we have the optical chip. Here we have our electronical chip. And here we use a grating coupler to couple in light to our chip. So why do you use silicon photonics? Okay, so not only does it give a small footprint, but also it allows us to integrate the optics as well as expensive electronics that we have in our experimental setup. It also allows for fast modulation, which is important as we are work at a high rate. Downside is that it's not as simple to integrate a laser here. And so we keep the laser external. The advantages here are that the expensive electronics like the digital to analog converter and the amplifier are replaced with this electronic circuit here. So here's an image of the structure of the chip. So maybe just one note, actually on the chip, the in and output are on the same side. Just for clarity, I placed them here on different sides. So we have precisely the same components as are needed for our protocol analysis side. So this means that we have an imbalanced Mach-Zehnder interferometer with a 200 picosecond delay line. We have here an absorber attenuator, which we can use that would simulate, so it would add loss in this arm to be able to maximize the visibility of this interferometer. Then we have an intensity modulator, which is based on a balanced Mach-Zehnder interferometer, which includes 3 electro-optic phase shifters, as well as heaters. So these are thermo-optic phase shifters that are in the arms. And finally, you have variable optical attenuators as well. So either the same absorption attenuator or a balanced Mach-Zehnder interferometer with thermo-optic phase shifters or heaters in each arm. Then going to Bob. So here Bob is based on silica, and it's fabricated in Milano in the group of Roberto Selame using the femtosecond laser micromachining technique. So here's an image of the structure of Bob, where we have the passive beam splitter going out to the Z, or this imbalanced interferometer with a 200 picosecond delay line. So this platform is chosen thanks to its low loss, very important on the receiver side, as well as this polarization insensitivity, which is something that's important for our protocol and complicated to achieve in photonic integrated circuits. Downside is that the detectors cannot be integrated. We use external single photon avalanche diodes and a relatively large footprint if one would compare to silicon photonics. So just an overview of the full experimental setup. We have an external laser, filter, the photonic integrated circuit. We have to place dispersion compensating fiber. Here we have Alice. We place single mode fiber, and then on Bob's we have this chip and external single photon detectors. So for the results, present here the result that we get from using our SPADs. So at a distance of 150 kilometers, we achieve a Q/Z of around 3.6%, a phasor array around 2.1%, and a secret key rate of around 2.9 kilobits per second. So what's interesting is to compare this result with the results obtained using the same detectors with our fiber-based system that was done in precisely this paper a few years ago. And so here we achieve a slightly lower Q/Z, similar phasor array, and thus a slightly higher secret key rate. This difference can mainly be attributed to the fact that we use a different detector parameters in the integrated scenario due to actually we have a 96 for splitting between the X and Z bases that is fixed in our chip. And so this, we were kind of forced to be heavily biased towards the Z bases, and sometimes we wouldn't have a high enough count in the X bases. But anyways, this we achieve very good results, very similar. So in conclusion, for the 3 experiments, we show that placing the quantum channel in the O band, having the classical channel in the C band, we can generate keys in a realistic scenario. We also achieve record high secret key rates and manage to integrate this QKD system at longer distances with competitive secret key rates and qubers. And so what's going on now in the lab? So one of the things that we're doing now is actually integrating our QKD system into a practical prototype. So this means that we have now taking a lot of effort of designing the PCBs, placing everything in a box. Notably for the detectors, now we use Peltier-cooled single photon detectors. Yeah, so this is ongoing work. And with that, I'd like to thank you very much for listening on behalf of our whole group and our Idée Quantique colleagues. I'm happy to take any questions.
Thank you very much, Rebecca. Questions?
Jan Krause, thank you very much for this nice talk, and there are really a lot of very nice results in it. I have a very specific question regarding your detectors. So for the X bases, you're just using one detector.
So you mean in general? Yeah.
I think all of the setups you showed,
yes,
you just
yes,
used
yes.
One detector.
Completely.
So basically, in all those cases where there's no detection, you kind of assume there would be one
in the other detector.
In the other arm. Does this open some loopholes that could be?
So, okay, if I'm not mistaken, we don't. So one can imagine that it's kind of it's redundant knowing. So in this detector, so the relative phase between the 2 interferometers is set such that the interference that arrives, so detection here does not exist, say. And so your question is that, is it a security loophole that the other detections, that we're not monitoring that?
Exactly.
Okay, of what I know, I don't think so. No, it is not a security loophole. Maybe more, further discussions would probably be from maybe Davide Ruska, who's here, but this is not something that I think so, yeah.
Okay, thanks.
Hi, thanks for the talk. Yeah, beautiful, beautiful work. You came to the conclusion that you want to send the quantum signals in the O band, at least over some distances. Since you're going co-propagating with the classical signals, I'm wondering if you did you look at all into doing basically time sharing so that the classical signals are not on at exactly the same time as the quantum signals, in which case then I could imagine that you might come to a different conclusion about what.
Okay, yeah, no, this we did not do. I'm aware, and it could change. And also for this, one important thing I did not mention for the counter-propagating and co-propagating case is that these graphs are for a fixed classical launch power. So of course, this would also change in a realistic scenario. One would probably like increase the classical power quite often to have this constant high power. And so then this situation would change a bit. But this we did not do.
Okay, great, thanks.
Hi, at the end of your third section, you had the graph about the detectors. I was wondering what the dead time on those detectors were. Is that known?
The dead time of the SNSPDs?
I think that was the SNSPDs.
Right. I think it was in the order of the recovery. Okay, I don't remember. In the order maybe of some microseconds or something like this. But maybe you can ask Giovanni for this.
I was just curious, do you have to worry about like after pulsing affecting any of your detection?
No, in the SNSPD case, this is negligible.
Okay.
If I remember, yeah. So this is completely negligible. It's probably even lower than the microsecond.
Thank you.
Thank you very much for your great talk. Can you briefly explain how the one decoy method can be better than the two decoy method, or is it generally, correct?
Maybe if I go to the graph just very quickly, I can give you some intuition if you want. I can try. Oops. So this is the case for a finite key scenario. So in the sense that in a finite key scenario, it's better, one can imagine, to have this one decoy because we don't have to estimate the vacuum states. And so we don't have to lose, if you want, detections for estimating this block of vacuum states. And this can be used for the key for the other just two. I'm not sure if that's clear. So in an asymptotic scenario, then we don't care about this. And then the two decoy would be okay, yeah. If that maybe is clear, yeah.
Okay, any further questions over there? Comes behind you.
Hi, thanks for the talk. On your metropolitan area experiment, were there multiple nodes in that experiment, or did you use a loopback fiber?
So when you mean multiple nodes, so we only had from Alice to Bob.
Sure, so were those two separate nodes separated by 100 or so kilometers?
Yeah, exactly. There was like, yeah. Exactly.
Did you employ some sort of time synchronization between those two nodes?
So to synchronize, yes. So this we have to do for the quantum channel to synchronize. But in terms of the classical channel, you mean?
For the quantum channel.
Yeah, for the this we do. Yeah, we actively synchronize via time tracking, if you want. So we use the empty bins where we, the next door bins to the ones that we're actually using for the detections to actively synchronize. Yeah.
Thank you.